section 3.7 is about rates of change. Instantaneous rates of change would be derivatives in the natural and social sciences. So it includes lots of examples of applications of calculus in the natural and social sciences. We're going to focus on, and I will only hold you responsible for, a physics application, which is position as a function of time. That's sort of the classic application of calculus that usually gets studied. That's not to say that the other applications are any less important or less interesting. That's simply to acknowledge that we have a limited amount of time, and that particularly in this online format, everything just seems to take a little bit longer. So I'm going to cut down a little bit on the content so that we can cover this one topic fairly thoroughly. I would encourage you, if you're interested in some of the other applications, to read through them on your own, and I'm certainly happy to answer questions about them. Okay. What we're going to be looking at is we're going to have t is equal to time, and that will be in seconds. I'm going to use p of t. The book usually calls it s of t, but I'm going to go with p of t for position, and that will be in meters. So the idea is here we've got some particle that's moving, and it's sort of going back and forth along some linear path. Now, because we're going to indicate direction with a sign, we only have two directions. So it's sort of like we've got a home position at 0, and if the particle moves to the right, it's moving in the positive direction. If it moves to the left, it's moving in the negative direction. So if I were here, if the particle were here, but moving this way, it would have a positive position because it's to the right of 0, but it would be moving in the negative direction. Okay, so I'm going to just work out with an example. Let's suppose that p of t is t minus 2 squared, and I'm going to be concerned with just the time interval from 0 to 4. So a 4-second interval studying a particle that's moving in this manner. Okay, so there are actually 4 functions that can describe this particle. The position function is one of them. We know that if we take the first derivative of position, we could call that the velocity. So I'm going to call that v of t, that's the velocity. And the units there would just be the fraction of these units, meters per second. We also know that if we take the second derivative of position with respect to time, that would be the first derivative of velocity, and the rate of change of velocity has its own name. That's a of t, which is the acceleration. And the units for that are the fraction of these units with the units for time, so it's meters per second, and we usually write that as meters per second squared. Now, I said there were 3 functions. There are actually infinitely many, because of course I could keep taking derivatives forever and ever and ever. Actually, I said there were 4 functions. Okay, there are infinitely many. Okay, here are 3 of them, the position function and the first 2 derivatives. The other one that we're going to be taking a look at in this section is not actually the third derivative, but is the absolute value of the first derivative, or the absolute value of the velocity. And that would be the speed of the particle. Now, the units for speed are the same as the units for velocity. The difference is that velocity is a signed quantity. Velocity can be negative, and when it's negative, that's going to indicate that the particle is moving in the negative direction. I'm going to just refer to that as moving to the left, supposing that we're moving on sort of a number line like so. Okay. Speed, on the other hand, is never negative because, of course, we're taking the absolute value here. Okay. So we're going to be working with all 4 of these functions. So what I want to do right now is just calculate these 4 functions for this particular position function. So we have the first one already, but I want to go ahead and calculate velocity, acceleration, and speed, and then we're going to be using those to answer a bunch of other questions about this example. Okay, so if p of t is t minus 2 squared, p prime of t, which is the velocity, is just going to be the derivative with respect to t of t minus 2 squared. I'm just going to do chain rule. Okay. I could, if I wanted to, multiply that out, but I think chain rule is going to be faster. I'm going to get 2 copies of t minus 2 times the derivative of the inside part. Now here, the derivative of t minus 2 is actually just 1. So I end up just getting t2 times t minus 2. I'm going to actually distribute that now and say that's 2t minus 4. Okay. So our velocity is 2t minus 4. Acceleration is going to be the second derivative. So I've got all these different ways of writing it. Second derivative of position, first derivative of velocity, or I can just call it the acceleration. That's just the derivative of 2t minus 4. Well, 2t minus 4 is just a line of slope 2, so that's just 2. So the acceleration here is just 2. I'm going to adjust this. It looked like I said meters per second was equal to this. I meant to say velocity was equal to this. So velocity was 2t minus 4. Acceleration is 2. And speed, we said, was just the absolute value of velocity. So that's going to be the absolute value of 2t minus 4. I didn't give a special name to the speed function, so I can either write out speed or I can write absolute value of velocity. Okay, so these are the formulas that we'll be working with. In the next video, we'll come back and we'll start answering some questions about the behavior of this particle.